Scattering of light. In this module, you will learn about the scattering of light and its effects. Sunlight is all around us, but we cannot see its rays everywhere. We can see the sun rays clearly when sunlight enters a dusty room. Do you know why this happens in a dusty room? This happens due to the scattering of light by the dust particles present in the dusty room. Small solid particles, here dust particles, suspend in a fluid, here air, are known as colloidal particles. The phenomenon of scattering of light by the colloidal particles is known as the Tyndall effect. The same effect can be observed when sunlight passes through the trees of a dense forest. Here, tiny water droplets in the mist scatter the light. Let us do an activity to observe the Tyndall effect. For this, place a strong source S of white light at the focus of a converging lens L1. This lens provides a parallel beam of light. Allow the light beam to pass through a transparent glass tank T containing clear water. Next, allow the beam of light to pass through a circular hole C made in a cardboard and obtain a sharp image of the circular hole on a screen MN using a second converging lens L2. As you can see, the path of the beam of light passing through the clear water, that is, true solution, is not visible. Next, dissolve about 200 grams of sodium thiosulfate or hypo in clean water in the tank. Add about 1 to 2 milliliters of concentrated sulfuric acid to the water. What do you observe? The path of the light becomes visible through this colloidal solution. In about 2 to 3 minutes, you will find fine microscopic sulfur particles precipitating. As the sulfur particles begin to form, you can observe blue light from the 3 sides of the glass tank. When viewed from the 4th side of the glass tank, facing the circular hole at first, an orange-red color and then a bright crimson-red color are observed on the screen. This happens due to the scattering of light by minute colloidal sulfur particles, that is, the Tyndall effect. The Tyndall effect can also be observed in the atmosphere and can explain some wonderful phenomena of nature, such as the white color of the clouds, the blue color of the sky, and the reddening of the sun at sunrise and sunset. The Earth's atmosphere is a mixture of minute particles. These particles include smoke, tiny water droplets, suspended particles of dust, and air molecules. When sunlight strikes these particles, it gets scattered by the particles, and the scattered light reaches us. The particles scatter a particular color of the scattered light, and the color of the light that gets scattered is the color of the light we see. Let us now understand how it makes the clouds appear white. The clouds consist of large water and ice particles. These large particles scatter all the 7 constituent colors of white light VIBGYOR equally. Thus, the light we see is the combination of all colors, that is, white light. This gives a white appearance to the clouds. Let us now come to the blue color of the sky. The molecules of air and other fine particles in the atmosphere are of very small size. These are more effective in scattering light of shorter wavelengths, that is, blue light. Thus, when sunlight passes through the atmosphere, the fine particles in the air scatter the blue color of shorter wavelengths more strongly than the red color of longer wavelengths. The scattered blue light enters our eyes, due to which we see the sky as blue. Let us now try to understand how scattering of light makes the sun appear red at sunrise or sunset. At the time of sunrise or sunset, the sun is near the horizon. The light from the sun near the horizon passes through a large distance in the Earth's atmosphere before reaching our eyes. While traveling through this large distance, the blue light scatters away in all directions before reaching our eyes. Thus, at the time of sunrise or sunset, the light that reaches our eyes is of longer wavelengths, that is, red, and the sun appears reddish. It will be interesting to know that if the Earth had no atmosphere, there would not have been any scattering. Then the sky would have looked dark. Let's recap. The path of light becomes clearly visible due to the scattering of light by the colloidal particles present in the path. The phenomenon of scattering of light by the colloidal particles is known as the Tyndall effect. The Tyndall effect can explain some wonderful phenomena of nature, such as white color of the clouds, blue color of the sky, reddening of the sun at sunrise and sunset. When sunlight strikes the minute particles present in the atmosphere, it gets scattered by the particles. The particles scatter a particular color of the sunlight that we see. The color of the scattered light also depends on the size of the particles. Smaller particles scatter lights of smaller wavelengths, that is, blue light, whereas larger particles scatter lights of all the colors equally.
Daily, morning to evening, we are seeing the sky. But anybody ask why sky is blue? No. The reason for this was found by Sir C.V. Raman in his wonderful experiment, that is a scattering of light. Scattering of light. For this, he got the Nobel Prize also. So, what is the scattering of light means? So, light absorbed by the small minute particles in the space and again re-emit out. The intensity of re-emitted light I is proportional to 1 by lambda to the power 4. That means 1 by wavelength, fourth power of wavelength. That means intensity is inversely proportional to fourth power of wavelength. As the wavelength increases, the intensity will decrease. So that is the concept here. So why the sky looks blue and why the sky looks red and orange in the morning and evening time? So these are all we see now in one small video in the descriptive way.
Some of the common questions that kids ask are, why is the sky blue while the clouds aren't? Why is the sun yellow? And why does it turn reddish-orange during sunrise and sunset? These questions might look difficult to answer at first. However, the physics behind them is not difficult at all. There are two things that play an important role in giving a color to the sky. One is the atmosphere of the Earth, and the other is the sunlight, of course. So we need to know more about these two first. The white light coming from the sun is a mixture of 7 primary colors, and each colored light has a corresponding frequency and wavelength associated with it. The violet colored light has the shortest wavelength of all, while the red one has the largest wavelength. And what forms the Earth's atmosphere? The Earth's atmosphere is mainly composed of gases, dust particles, water droplets, and water vapor. Among the gases, nitrogen is present in abundant quantity at around 78%. It is followed by oxygen, which is approximately 21%, and the remaining is filled with the likes of argon, carbon dioxide, and other gases. First, let's see what happens when the sunlight falls on these air molecules. When sunlight strikes these molecules, it gets scattered. Scattering is a process in which the light is absorbed by the atoms and re-emitted back in various directions. However, not all the light is scattered equally. The amount of light that will be scattered is given by the Rayleigh law of scattering. It says that the amount of scattered light or the intensity of the scattered light is inversely proportional to the fourth power of the wavelength of a wave. I is inversely proportional to lambda to the fourth power. If the value of lambda increases, then the intensity will be lower. If its value decreases, then the intensity of scattering will be more. Lesser the wavelength, more will be the scattering. So now, I want you to tell me, among the 7 colors of sunlight, which one will be scattered the most? Yes, the light of the color corresponding to the smallest wavelength will be scattered the most. So blue, indigo and violet light will be scattered most by these molecules of air. And when this light travels to our eyes, the sky appears blue to us. But wait, the violet light has the smallest wavelength. Then why doesn't the sky appear violet or even indigo for that matter? It is true that the sky scatters the violet light more than the blue light. However, we don't see violet sky, do we? What's the reason? The following graph tells us how much of a particular wavelength is emitted by the sun. Observe the graph well. As you can see, the sun emits more blue and light bluish light compared to the violet light. Hence, more blue light is scattered by the air molecules, resulting in the blue color of the sky. And another reason why we cannot see violet light is because our eyes are more sensitive to blue light than to violet light. So this was about how the gases present in the atmosphere scatter light. Do dust particles and water droplets also scatter light? Yes, they do. They scatter light as well. However, their size is comparatively much bigger than the size of the light waves. And hence they scatter all the colors of light in equal amounts. So the white light which is entering the cloud or the dust particles emerges out as white light again. Hence the clouds appear white. There's one last question we need to answer. Why does the sun appear reddish during sunset and yellow otherwise? We will